All right, everyone. So we've spoken a lot about rate equations and what they are, but now how do we determine a rate equation? And the typical way of determining it is by using the method of initial rates. There's also a different method. There's a logarithmic method or a graphical method, but the method that we will look at is the method of initial rates. And this is always best illustrated by some examples. So I'm not going to do this example, I'll do that one in class. So I have some play data here for us. So where I ask, how do you determine a rate equation? So let's say you have a rate or a reaction that goes A plus B gives C. And you want to determine its rate. So meaning what is rate? If you have to write the rate law for this, you would say the rate is equal to the proportionality constant K equals to the concentrations of the reactants to the powers of something that you don't know, right? So A to the power M multiplied by B to the power N. So in other words, you just take the two reactants and you put down their concentrations and you put them to the power of something that so meaning an M and an N, because you don't know what those powers are right yet. Okay, so that's what we want to know. What is the rate equation for this general reaction? And what you typically do is you do a couple of experiments. In those experiments, then what you do is you vary the initial concentration of those reactants. So see, in each of these reactions, you vary the initial concentration. So that's what the zeros mean. It means the initial concentration of A and B. So let me just take that away. Um, and you'll notice something specific about it just now. So you vary the concentrations of the reactants to see how the rate, the initial rate of the reaction varies. So in other words, you want to see literally, if I change the reactant concentration, how does the rate vary? So meaning that question that I asked way back at the beginning, if I vary the reactant concentration, see how the rate responds. All right, so that's literally what we're trying to do now. If I vary the concentration, what happens? Okay, and we need to set up these experiments um, quite uh, well, because what will happen if we vary both of the reactant concentrations at the same time? Would we get any useful information about the reaction? Yeah, I mean, we would know that the rate will probably increase or something will happen, but we won't get any useful information about either B or either A, right? So that what would be a more useful study is if we set up reactions whereby, or experiments whereby you increase the concentration of one. So meaning if you look at experiment 1 and 3, so look, I doubled the concentration of reactant A, so going from 5 to 10, but reactant B, I use the same concentration in those two experiments. So this one is times 2, this one is same concentration. So hence, whatever the change is here in the rate is because of A. Aha, right? So that's typically how we do it. You keep one thing constant and you vary the other thing, and you see what the response is of the system. And that then gives you some practical information that you can do something with. And what happens here actually? So what happened here to the system? You can see the rate doubled. It went from 100 to 200. So you can see there is a multiplying by 2. So we'll talk about that just now. In the same vein, if you look at experiment 1 and 2, this one, I kept it the same, and B, I doubled. So in other words, in this case, we double B, and what happened to the rate? In this case, the rate is quadrupled. So the rate went multiplied by 4. All right, so you can see by doubling A, the rate only doubles. By doubling B, the rate quadruples. All right, so you can clearly see that B has a greater effect on the rate than what A has. Okay, so let's perhaps summarize this information for ourselves. Where's a better place to write this? So, experiment 1 and 3. Keep it in the blue. And this is the effect of A. So in experiment 1 and 3, we said the concentration of A is doubled. The concentration of B is the same, right? And the rate is doubled. So what does that mean? That means the rate and the concentration of A, or the reactant A, has a 1-to-1 relationship. So meaning if I double the one, the other one doubles. If I triple the one, the other one will triple. If I, whatever I do with the one, exactly the same happens to the other one. And what kind of relationship in terms of a power happens, or will that mean? So in other words, exactly if I put the number that I put here happens to be the number that I put there. It only happens if the number that I have here is a 1, right? So meaning the only way that I get a 2 here and a 2 here is if I have 2 to the power 1, right? I can't have a 2 on both sides if I had 2 to the power 2, for example. Then I would get a 4 on the left-hand side. So therefore, it means that the power m has to be 1. Okay, that's basically what I was getting to, because there's a 1-to-1 relationship at how the initial rate varies as how A varies. You can literally see that in the data. Because A is doubled, the initial rate doubles. Okay, that doesn't exactly make sense. Maybe if we look at B, it will make a bit more sense. Now, if we look at experiments 1 and 2, the concentration of A, right, this time remains the same. The concentration of B was doubled. And what happened with the rate? Oh, this time the rate was multiplied by 4. It quadrupled. So that means that the rate and B has a what-to-what relationship. You can write it as it has a 2-to-4 relationship, but the base number for 2-to-4 is it has a, it's the other way out. But the other way around, it has a 4-to-2 relationship because it's rate to B. So that means it has a 2-to-1 relationship. And the only way then that rate will be 4 if I write a 2 here is if I have 2 to the power 2. All right. And hence, that means that n has to be 2. because if I doubled, right, if I double B, the only way that this can be multiplied by 4, so in other words, to get a 4 on the left-hand side, is if this thing was squared. Okay, that means n has to be 2. The same way as the only way that if I had multiplied by 2 here, the only way that this could have been multiplied by 2 here, so 2 here, the only way to get a 2 on this side is to have 2 to the power 1. So that makes m a 1. All right, so that makes the reaction first order in A, and it makes it second order in B. And finally, we have rate equals K A squared B, oh no, not A squared, just KA, B squared, and therefore it is third order overall. And that's then how you determine a rate law. You can then go ahead and plug in any of these data sets. So you choose a rate, you choose a concentration and a concentration, and then you can solve for K. But that's something that we will look at in class. Okay, so I hope this gave you an idea of how you can see how the concentration relates to the rate and then how you get the order in terms of a reactant. Okay, or how it basically tells you the M and the N value, because that's what it tells you. It tells you the order in terms of that reactant. How does the rate respond in terms of that reactant? If it's the same, so meaning you can see there's a one-to-one relationship, it means it's first order in that reactant. If the reactant has, so meaning you double the reactant, but the rate is quadruple, so meaning the rate responds double for whatever the change in the reactant is, it means it is second order in that reactant, right? So, and this is how you can see any kind of relationship. So let's say, for example, you doubled the reactant concentration, but the rate halved. What would the relationship then be? I mean, you can go and think about these kinds of relationships, how they manifest. All right, but that's how you determine a rate law. And I mean, this data is of course just made up. I just made it up to try and illustrate the point. Cool. I'll see you in the next video, and thank you as always for watching. Okay, there's a very important addendum, appendix that I need to add to the previous video that I realized. This was, as I mentioned, it was play data that I wanted to add. And it was a way that I want you to visualize how to analyze data. So meaning, for example, like this table that you typically will have, and you can analyze this data and you can look at it as such. There is a proper way of doing it and using logarithms, etc., that we will use to do it. And you will solve, for example, n using logs, and you will get the actual value, meaning 2 and 1, etc., using your logarithms. So you will not eyeball it as what I eyeballed it here, so you don't have to worry about that as such. This is just a way for you to visualize or to see, this is the effect of concentration on initial rate. So this is not an official method of doing problems. It was a teaching moment. So please take it as such. Do not solve your problems like this. I repeat, do not solve your problems like this. It is a good way to understand the work um, before you tackle the problems like we will do in the lecture. Okay, so please take it as such. All right, now thank you for watching.